Hello, welcome to another session of engineering mechanics. In this subject, we are currently dealing with the chapter of moment of inertia. Here, initially, we have defined what is moment of inertia, how we get the concept of moment of inertia from three-dimensional bodies and how we extend it to the two-dimensional lamina or two-dimensional bodies, that is two-dimensional areas, and we have found out the moment of inertia of a rectangle using that concept, that is using the concept of second moment of areas, that is area into distance, and we have used that concept and we have derived formula for a rectangular lambda, that is by taking a small strip dy at a distance of y from the centroid, and we have found out the second moment of area of that strip, and we have integrated all such strips to get the entire rectangular area. Then we got this I of a rectangle about its y-axis is centroidal y-axis is x-axis BD cube by 12, and about the centroidal y-axis as DB cube by 12. We have seen in the earlier class, and also we have seen what is radius of gyration, that is the concept of radius of gyration we have seen, and also we have dealt with the theories of moment of inertia, that is in moment of inertia we have parallel axis theorem and perpendicular axis theorem. In parallel axis theorem, if we want to find out the moment of inertia about any axis which is parallel to the centroid axis, then what we have to do? That theorem says that we have to add the another component of moment of inertia equal to the area of that figure into the distance between the new axis and the original centroid axis. That is, by knowing the area into the distance, we have to move that d into square of the distance, will give you AD square or AH square depending upon the direction which we are taking. So sum of the new moment of area is equal to sum of the moment of area about centroid axis and also the square of the distance into area of that figure. That is, we have seen in case of a rectangular area, that is of B into D, we have moved from the centroid axis x to CC, some new axis CC. So for that we have used the parallel axis theorem, that is I about CC, the new axis, is equal to IXX, the moment of inertia about x-axis at the centroid, plus area into the h square, that is the distance between the two parallel axes, that is this x and c, the distance between x and c is d by 2, therefore we have put h is equal to d by 2, therefore we got the moment of inertia of a rectangle about its base as BD cube by 3. Similarly, if we take any side that is along the y-axis, then it would be dB cube by 3. That we can do it in the perpendicular axis. Similarly, we have seen some problems about on T section, that is symmetrical about y-axis, a C section that is symmetrical about x-axis, and also we have also seen the unsymmetrical C section, that is it is neither symmetrical about x or axis or y-axis, so it is not symmetrical in any axis. Then also we have seen found out the moment of inertia about the centroidal axis of that C, that is the centroid was at 32.27 and 33.63 from the bottom corner of the figure. So from here it is 32.27 in x direction and 33.63 in y direction. That was the centroid of the unsymmetrical C section. And for that we have found out the moment of inertia, that is about centroid. It is 2.06 into 10 to the power of 6 mm to the power of 4 and 1.78 into 10 to the power of 6 mm to the power of 4. These are the two moments of inertias about x-axis and y-axis respectively. That is all we have done till now in this chapter. Now further moving ahead, we go to another type of problem. That is, let us say deal the problem of a hollow rectangular section. That is, there is some rectangular section of B into D, out of which a small b into small d, that is some portion is cut off. Then we are left with the hollow rectangular lamina, that is we are only left with some strips along the borders. So now our problem is to find out the moment of inertia of this hollow rectangular portion which doesn't have this central portion. It is, but both are, the removed portion and the actual outer portion are symmetrical about both axes. That is, the portion which is removed from the rectangle is also symmetrical about its y-axis and x-axis. Therefore, since both the rectangles are symmetrical, the centroid lies at d by 2 and d by 2. That is, for outer rectangle it is d by 2 and d by 2. For inner rectangle also it is d by 2 and d by 2. Therefore, the centroid of the entire hollow figure will be equal to b by 2 and d by 2 automatically. That is, since they are symmetrical, all the three figures, that is the outer rectangle, the inner rectangle and the compound figure, are symmetrical about y-axis and z-axis, y-axis and x-axis. Therefore, the x and y will be b by 2 and d by 2. That is, all are symmetrical. Therefore, we will see the moments of inertia of individual figures. That is, for outer rectangle, the breadth is b, depth is capital D. Small capital B and capital D are its dimensions. Therefore, Ix of outer is I outer of x and so we have found out the Ix and Iy of the outer rectangle, that is I outer x and I outer y, outer rectangle, that is bdq by 12 and bdq by 12, which are capitals. That is, capital B into dq by 12 is its Ixx and Iyy is dbq by 12. Similarly, for inner circle it is small bdq by 12 and small dbq by 12. These are the moments of inertias, and we know that for compound section we have to take the sigma Ixx plus sigma Ah square. That is Ix of the compound figure is equal to individual moments of inertia plus areas into distances squares we have to take. Therefore, now here sigma is algebraic sum, that is the outer from the outer from the outer rectangle we have removed the inner rectangle. Therefore, we are taking Ix of outer minus Ix of inner plus area of outer rectangle into h, that is the distance of the centroid of the outer rectangle with respect to the overall figure, that is overall compound figure. Similarly, minus area of inner rectangle into the distance between its centroid to the overall centroidal distance, overall centroid of the hollow rectangle. Therefore, we get similarly ICY, we get sigma IYY plus sigma AD square, that is IY of outer plus IY minus IY of inner plus AO into DO square minus area into distance square of the inner. So therefore, since y minus y0, that is the distance of centroid lies at d by 2. Similarly, centroid of the outer rectangle also is at d by 2. Therefore, the y minus y bar is d by 2 minus d by 2. Similarly, hi is equal to y minus y1 y inner, that is d by 2 minus d by 2. Therefore, there is all the three centroidal axis, that is centroidal axis of the outer rectangle, centroid axis of the inner rectangle, and centroid axis of the entire figure. They are all lying on the same x-axis. Therefore, the distance h0 and ho and hi are zeros. Similarly, d0 and dy, that is the horizontal distance between the y-axis. The actual y-axis is at b by 2 of the entire figure. Similarly, for the outer figure also it is b by 2. For the inner rectangle also it is b by 2. Therefore, their distances also they are 0 and 0. Therefore, the net ICX, that is I moment of inertia about centroid in x direction, is Ix0 minus Ixi, that is Ix of outer rectangle minus Ix of inner rectangle plus area of the outer rectangle into distance between centroidal axis in y direction, that is they are x axis, so the distance between x axis will be y. So a0 into a outer into h outer square minus a inner into h inner square. But since h outer and h inner are zeros, we will be left with only bd cube by 12 minus small bd cube by 12. Therefore, I about centroidal x-axis is bd cube minus small bd cube by 12. Similarly, if we take ICY, IY of outer minus IYY of inner plus A of outer into DO square minus A of inner into DI square. But DO and DI are zeros. We have shown here. Therefore, we will be left with only dB cube by 12 minus small dB cube by 12. Therefore, it is dB cube minus small dB cube by 12. Finally, the moments of inertia of hollow rectangular section will be bd cube minus small bd cube by 12, and in y direction it will be dB cube minus small dB cube by 12. So this is how we will arrive at the formula for moments of inertia of a hollow rectangular section. So simply we are nothing, we are doing nothing. We are simply finding out the moment of inertia outer rectangle, that is BD cube. Similarly, for the inner rectangle it is small BD cube. So difference will give you BD cube minus BD cube. Similarly, in y direction it will be dB cube minus small dB cube by 12. So this is one example I have taken to show you how the symmetrical, if some symmetrical rectangle is there, symmetrical hollow rectangle is there, then how to find out the moments of inertia. So we have to remember this, that for hollow rectangle, the I xx about its centroid, that is why we have designated as I centroidal x-axis is equal to BD cube minus BD cube by 12, that is capital BD cube minus small BD cube by 12, but and ICY is capital DB cube minus, that is outer areas moment of inertia about y minus inner areas moment of inertia about y, that is dB cube, capital DB cube for outer rectangle and small dB cube for inner rectangle, that is it is nothing but capital DB cube minus small dB cube by 12. Now we will move on to another common section which we use in our civil engineering, that is in I section. Generally we use I sections for beams because their moments of inertia are in y direction and x direction are very different, and we have large moment of inertia in x direction and smaller moment of inertia in y direction. Therefore these generally beams are used for I sections are used for beams. So we will see a small example, that is a symmetrical I section which has flanges of 100 into 10 100 into 10 and a web of 10 into 180 and also bottom flange of 100 into 10. This is the shape of the I section, that is the top two flanges are 100 into 100 mm into 10 mm and the web is 180 into 10 mm, that is overall section is 100 into 200, that is overall flange width is 100, overall height is 200. In that we have removed 10 and 10 for flanges, the web will be only 10 into 180. Since section is I is symmetrical about both vertical axis and horizontal axis, simply we are not finding any centroid. We know that for symmetrical axis the centroid will be at the axis which are cutting the figure into two equal parts. So both y-axis and x-axis are cutting the figure into two equal halves, so the meeting point will be the centroid of the I section. Therefore the centroid will be 50 and 100. Here in this direction it is 50. In along the x-axis, if x-axis cuts it into two equal halves, then that x-axis will be at 200 by 2, that is 100. Therefore y bar will be 100 and x will be 50. That is y-axis is cutting the I section into two channels of 50 and 50. Therefore x bar will be 50. Similarly x-axis is cutting into two T sections, two symmetrical T sections, that is at a height of 100. Therefore we are getting 50 and 100. This is the first stage. The second stage will be we have to find the moments of inertia of individual components. Stage 2, calculation of moments of inertia of the components. So first we are finding the bottom flange, that is the first one. We have given the number as 1 for that component. Therefore, for the first component, it is a bottom flange. The horizontal is 100, the vertical height is 10, horizontal distance is 100. Therefore, Ix1, Ix of first will be BD cube by 12, that is 100 into 10 cube by 12, that is 8333.33 mm to the power of 4. Similarly, along the y-axis, then D is 10, B is 100, so it is 10 into 100 cube by 12, that is 8,33,333.33 mm to the power of 4. So this is for the bottom flange. Similarly, for the web thickness is 10, the height is 180 mm. Therefore, B is 10, D is 180. So BD cube by 12, Ix of 2 is BD cube by 12, that is 10 into 180 cube by 12. It is 486,000, that is 4,86,000 mm to the power of 4. Similarly, if we measure the moment of inertia about y-axis, then I by 2 is equal to dB cube by 12, D is 180, B is 10. So 180 into 10 cube by 12, that is 15,000 mm4. Similarly, since it is symmetrical, the third component is also a top flange. Therefore, it will be same as the bottom flange. The moment of inertia will be same as bottom flange, that is BD cube by 12 is 100 into 10 cube by 12, that is 833.33 mm4, 8,333.33 mm4. Similarly, I by 3 is dB cube by 12, that is 10 into 100 cube by 12, that is 8,33,333.33 mm4. These are all the individual moments of inertia of top flange, bottom flange and the web. So, these moments are about their centroidal axis or axis of their individual centroids. That is, for flange, for web and the bottom flange, we have found out the moments of inertia about the centroids. But now our aim is to shift these moments to the actual centroid of the entire figure. So individually they are located at their individual centroids, but the overall centroid of the figure is different from their centroids. So our problem is now to shift those moments of inertia from their own centroids to the common centroid of the combined figure. Therefore, we have to know how far we have to shift, that is how far their axes are located from the centroidal axis, that is x-axis of the top flange, x-axis of the bottom flange and x-axis of the web, those distances from the actual centroidal axis of the entire figure. Therefore, we have to find the H1, H2 and H3, because our formula says that ICX is equal to sigma IXX plus AH square, where H is the distance between the parallel x-axis, that is the axes which are in the x direction. We have to take the distance from the common compound x-axis. Therefore, here if we see this figure, the x-axis of the compound figure lies at a distance of 100 from the base. 100 from the base. Similarly, from the base, the flange x-axis is at 5. For web, it is at a distance of 100. from the base. For third figure, it is at 195, that is y bar of the that figure is for the top flange is 195. Of the base. So the distance h1 will be 195 minus 100. That will give you the h1, that is 95. Therefore, here if we see the equation, h1 is equal to y minus y1, that is y of the common figure is 100, y1, the y of the bottom flange is 5 at 5, so it is 95, y of the web is 100, y2, the y2 of the web is at 100, so it is 0. We need not shift the moment of inertia about x-axis of the web to any new axis, because both the centroidal axis of the web and also the centroidal axis of the compound figures are lying on the same, along the same line, that is along the 100. So it is 0. Similarly, y minus y3 is 195 minus 100, that is 95. Therefore, in the next stage, we are finding the actual moment of inertia of the entire figure, that is ICX is equal to sigma IXX plus AH square, sigma AH square. Therefore, ICX is IXX of first figure plus IXX of second figure, IXX of the third figure, that is the flange, web and flange, plus area of the first figure, that is bottom flange, into height to which we have to shift, or the height at which we have to find out the new moment of inertia of the flange, and moment of inertia of the web we have to add for shifting the web, and also for shifting the flange, that is we are finding the moment of inertia at a new axis from its own centroidal axis. Therefore, we have to add AH square, the first third component, h3 into h3 square. Therefore, we have found out earlier the IXX1, IXX2 and IXX3, that is 8,333.33, 486,000 and another 8,333.33. These are the individual IXX, plus areas are the first, the bottom flange is, area is 10 into 100 into 10 into 100 into 95 square, or I should say 100 into 10 into 95 square, because 100 we are taking x as 100, so 100 into 90 into 95 square plus 10 into 180 into 0 square plus 100 into 10 into 95 square. So if we calculate these values, it will come to 22.93 into 10 to the power of 6 mm4. So by adding IXX1, IXX2, IXX3 plus AH1 square plus AH2 square plus AH3 square, we get the sum as 2,29,26,666.66 mm4, that we are expressing in terms of units of 22.93 into 10 to the power of 6 mm4. Similarly, if we see the next figure, the d1 of the flange is, that is the y-axis, that is x bar. X bar is at 50, d2 is also at 50, d3 is also at 50, and common x is 50. Therefore, since they are all are symmetrical, we get d1, d2, d3 as zeros. We will see in this equation. That is ICY is equal to sigma IYY plus sigma AD square, where if we expand it, ICY is equal to IYY1 or IY1 plus IY2 plus IY3, that is moment of inertia of first component about y-axis, second component about its y-axis, and third component also about y-axis. That is 3 moments of areas about y-axis, and also area into distance between their y-axis and the actual centroidal axis. That is centroidal axis is at a distance of 50. That is y-axis are vertical, their distances are horizontal. So x will be 50. So therefore x minus x1 is 50 minus 50, that is 0. X minus x2 is 50 minus 50, that is also equal to 0. Similarly, d3, x minus x3 also 50. 50 minus 50, 0. That means there is no scope of finding the moment of inertia of these 3 components. That mean that we need not find any new moment of inertia. That is, since their moments of inertia are lying on the same axis, which is same as the centroidal axis, so there is no scope to use the parallel axis theorem, because we are not shifting to any new other axis, because the centroidal axis of their own, that is the centroidal axis of the components and also the centroidal axis of the entire figure are lying on the same axis. Therefore there is no scope for finding moment of inertia about any other parallel axis. They are lying in the same axis. Therefore these distances will be equal to 0. Therefore we cannot have any additional moments for shifting them to the new axis. We are not actually shifting them to any new axis. They are at the same axis along the centroidal axis. Therefore IYY1 is 8,33,333.33. IY2 is 15,000. IY3 is again 8,33,333.33, and this area is 100 into 10. Distance is 0 because we are not finding any moment of inertia about any new axis. The same centroidal axis itself is the axis where we have to find the moment of inertia. Therefore this is 0. d2 is also equal to 0. d3 is also equal to 0. Therefore these only we are left with only these 3 IYYs, that is IYY about their individual centroids. Therefore by adding them we get 16,81,666.67. that is 1.68 into 10 to the power of 6 mm4. So we have found out the moments of inertia of a symmetrical I section about its centroid, that is about 50, 100, that is x and y are at a distance of 50 and 100 from this origin 0, 0. Therefore there the moment of inertia of the compound I section, that is with one web and 2 symmetrical flanges, we have the moment of inertia as 22.93 into 10 to the power of 6 and 1.68 into 10 to the power of 6 mm4. If we observe, along the x-axis it is 22.93, along the y-axis it is 1.68. So when we load it, these beams are very effective in bearing the load and giving the bending. So in higher classes you will calculate the bending stresses and how much deflection it is the beam has taken. So in those cases we will see that this more Ixx is beneficial to us, that is the less Iyy and moment of inertia in y direction and more in the x direction will give you better characteristics for the beam. Therefore I sections are commonly adopted in design of beams. This property of higher moment of inertia along x-axis and lesser moment of inertia about y-axis gives an advantage to the I sections for using them as beams. So most common beam sections are I sections. This property of higher moment of inertia in along x-axis and lesser moment along the y-axis gives them edge over the other sections. That is why I sections are most commonly used beam sections. Let us see an example about the hollow rectangular section. That is, we have seen the case of hollow rectangular section using the width b of the outer width b and inner width small b and outer height or depth capital D and inner portion depth as small d. Now we will see the numerical example by giving them values. That is, the outer width of the outer rectangle is 100, height of outer rectangle is 200 and inner rectangle is 90 and 180. I have taken these values purposefully because I want to demonstrate the relationship between the hollow rectangle and an I section. So here if we see this I section, simply I have divided this web of 10 mm into two parts of 20 mm because its area was so that web of 10 I have divided into 5 and 5. So now I have this I where the web is divided into 5 and 5, that is 10, it is divided into 5 and 5 and shifted to the corners of the flanges so as to form a rectangular symmetrical hollow section. So by now we know that what are the moments of area of the hollow rectangular section. That is, we know it is BD cube minus BD cube by 12 and DB cube minus DB cube by 12. Therefore, finding the capital BD cube, that is Ixx of outer rectangle, that is 100 into 200 cube by 12, that is this much, 6 crores 66 lakhs 66,000 and 666.67 mm4. Similarly, dB cube will be equal to 200 into 100 cube by 12. The value will be 1 crore 66 lakhs 66,000 and 666. That is, there is a difference of almost 6 times between them, at least 5 times. Similarly, if we take the inner angle, Ixx of inner rectangle will be small bd cube by 12, that is 90 into 180 cube by 12, that is 4374 followed by 4 zeros. Similarly, Iyy of inner rectangle will be small db cube by 12, that is 180 into 90 cube by 12. If you see, it is outer x-axis, outer Ixx will be 100 into 200 cube by 12, and Iyy will be 200 into 100 cube by 12. Similarly, for inner one, 90 into 180 cube by 12 will be the Ixx, and Iyy will be 180 into 90 cube by 12. That is what we got here. 180 into 90 cube by 12, 90 into 180 cube by 12, 100 into 200 cube by 12, and 200 into 100 cube by 12. These are the values for them. So, sigma I about composite section or the entire hollow section is equal to sigma Ixx plus sigma AH square. So, it is Ixx of inner minus Ixx of outer minus Ixx of inner plus area of outer into h square minus area of inner into the hi square. That is the distance between its centroid axis and the common this. Since d1 and d2 y and y0 are same, x and x0, y and y1 are same. Similarly, x minus x0 is also 0. We know that finally the moment of inertia will be bd cube minus bd cube by 12. I see x is equal to bd cube minus bd cube by 12. I see y is equal to db cube minus db cube by 12. The values we got as I see x as here 2,29,26,666.67 mm4. Here we got 57 lakhs, that is 1,666.67. That is 22.93 into 10 to the power 6 mm4, and ICY is 5.73 into 10 to the power 6. These are values which we have got about the centroid axis of the common figure, that is the compound figure, which is the hollow rectangular section. So here we have some observations. We compare this rectangle, this hollow rectangle, and the I section, this hollow rectangle section and the I section. So they have some commonalities, that is they have some common things between them. That is, if we observe, the moment of inertia of I section about axis at the centroid are, for I section it is 22.93 into 10 to the power 6, ICY is 1.68 into 10 to the power 6. If the two halves of the web are moved along the x-axis to make a hollow rectangular section of the same area, from the centroid, the H1 and H2 have not changed because we have changed them in the horizontal direction. So horizontally we have shifted, vertically they have not moved. So y minus y1 remained the same. Therefore, there is no change in its moment of inertia along the x-axis. Therefore, we get Ixx of I centroidal x of I section and I centroidal about the x-axis of rectangle as 22.93 into 10 to the power 6 mm4. That is, the I is not changed. Moment of inertia about the x-axis is not changed by changing the shape of the I section. I section I have bifurcated the web and shifted it to the corners. So thereby making it a hollow rectangular section. By doing that, the moment of inertia about the x-axis has not changed. For both of them, it remained 22.93 into 10 to the power 6. But if we see the Iyy of I section is 1.68 into 10 to the power 6, but for rectangular section it is 5.73 into 10 to the power 6. That is almost there is a change of 5 times. simply by cutting the web of I section and shifting it to at a distance that is from centroid, from common centroid to the corners of the flange, that is at a distance of 45 mm. That is here, if you see this I section, these 5 are from here to here, they have been shifted. That is, they are shifted by 45 mm here and 45 mm there. Therefore, their centroids are shifted by 45 mm. Hence, the IC of Y has changed from 1.68 to 5.73. That is, there is change in moment of inertia along the y-axis of the I section, and also there is a change. It is different from the IYY of a hollow rectangle. So, the earlier it was 1.68. Now for rectangle it is 5.73 into 10 to the power 6. So there has been a very vast change in moment of inertia. So we can conclude that when the I section is similar to hollow rectangular section in case of IXX, but not in the case of IYY. So we can treat an I section as a hollow rectangular section in case of only IYY, but not in IXX. I am sorry. That is, along the IXX, the hollow rectangular section and I are same, but along y-axis they are different. So in the higher classes, that is for finding the bending stresses or for finding the deflection of beams, we need to find the moment of inertia of I section, symmetrical I section. Many times we do. So for finding the symmetrical moment of inertia of I section, we need not do entire process of finding the centroid, finding out the moment of individual moments of inertias, adding them, all those things. Simply by assuming the I section as equivalent rectangular section, we can find IXX by simply BD cube minus BD cube by 12. That is capital BD cube minus, that is outer area minus inner area. That is, outer area's moment of inertia will be capital BD cube by 12 minus inner area's small BD cube by 12. This is how we can use this concept of hollow rectangular section, which can be extended to the symmetrical I section. But this only works in case of the IXX, not the IYY. That we have seen with the example of the I section which is made into a hollow rectangular section. So in this class we have seen a concept of the moment of inertia of a hollow rectangular section, and we found out that the moment of inertia of symmetrical hollow rectangular section is capital BD cube minus small BD cube by 12. And also we have found out the moment of inertia of a symmetrical I section, and also we have made a hollow rectangular section out of this I section by bifurcating the web and shifting them to the edges of the flange. Thereby the same area will be there, but the figure has changed to a hollow rectangular section, and we have found out the moment of inertia about the x-axis and also moment of inertia about the y-axis. If we compare them, coincidentally for ixx they are same, but for iyy they are different. Therefore we can conclude that when we come across moment of inertia of I section about ixx, we can take help of this concept, that is treating I section as a hollow rectangular section of the same area, same symmetrical area, and we can use it for finding the ixx by using the formula which is very simple, that is bd cube minus small bd cube by 12. Therefore this concept will be handy in finding the moment of inertia about x-axis, but it cannot be extended to y-axis. But generally in strength of materials and other subjects, there is necessity of finding the moment of inertia about x-axis only. Then in such cases we can use this concept and we can easily solve the problem, because this finding out the moment of inertia involves finding the centroids, then finding the moments of inertia of individual components, adding them by knowing the distance of their parallel axis, and it is a tedious procedure. So to avoid that, we can use this shortcut in case wherever we can use it. So with this I'll conclude this session. In the next session we will be seeing the moments of inertia of some other shapes. Till now we have seen only about the rectangles. We will see the moments of inertia of some triangles, circles, semicircles and quadrants of the circles in the next session. So till then, have a nice day. I hope you enjoyed this class and I hope it is beneficial to you for enhancing the knowledge of engineering mechanics, particularly in the topic of moment of inertia. Thank you.